Hello, everyone. As usual, we will start at around 11:10. And today, the full lecture will be dedicated to their exam on December 12th. If you have any questions before the lecture starts, please send your messages into the chat. See you in 8 minutes. Okay, so let's start. Can you guys hear me well? Okay. So first of all, there is no new material, as I said several times before. The whole lecture today will be dedicated to the exam. So I hope you guys can ask questions, right? I'm gonna go through some big problems, right, with you. And I'm gonna go slowly and you should ask questions. Again, remember, I'm doing this for your benefit. So I expect it's not gonna be just I'm talking to myself, but you should ask questions if something is not clear, okay? So this is the whole plan for today. We're probably gonna finish early, depending on how many questions we have. And then I would be happy to answer some of the questions that you might have while preparing to the exam. Okay, any questions before we start? Is everything clear? Again, as usual, if at least some of you can turn on your cameras, that would be helpful. And maybe even for some questions, if it's easier and you want to ask it, I will unmute you and you can ask your questions with your voice if you prefer this way. So just send the message, because sometimes if it's not a trivial question, that would be better. Okay. Okay, let's start then. So reasons. Let me. Okay. Okay, let's go. So first of all, I'll repeat once again, because I guess no matter how many times I say it, people still ask this question. So how long is the exam and everything? So first of all, exam is going to be on Quarkus, and it will start at the time specified in the exams, which is 8 p.m. on December 12th. So I hope everyone's seen your schedule. That question was asked multiple times on Piazza. Hope everyone figured it by now, right? So even though the reserved load is for 3 hours, right? We're not gonna have a 3-hour exam. It's gonna be 90-minute exam, okay? So it's gonna have different types of questions. It's gonna have shorter questions that are really trivial. That is like multiple choice questions that you had on quiz, right? Which should take you less than a minute to answer, or maybe seconds to answer, right? Just test your knowledge. There are going to be a lot of those small questions, and that's going to be the first part of the quiz. Then there are going to be questions that are medium in size, where you typically might need to type in some answers, maybe also choice selection, but usually we need to type something, right? So please be ready for that, right? And there are going to be some questions where you might need, we're still looking at how to do it more convenient for you, but there might be some questions you need to write on the piece of paper and then upload an image. We're going to have very few questions like that, but there's going to be some. And I'll show you examples like that. So what's going to happen for those questions, you would have to upload an image. You don't have to wait until the end of the exam. So essentially you could, for example, there can be a question, it doesn't need to be on the paper, by the way. You can use the tools, the editors. So essentially we're going to give, for example, a question, and you might need to highlight something on the image, right? So you can use it, you know, either any of the editors with the JPEG files, anything that's convenient for you, right? And then you upload the file back, okay? And just for that specific question, right? And you don't wait until the exam, because there were some exams where they upload everything at the end and there were some glitches because of that on the system. Try to avoid that so you don't get stuck. Okay. So essentially this is on the logistic of the exam. In parallel, as you write the exam, we're gonna have a Zoom meeting running. And in this Zoom meeting, right, it's gonna be similar. Can you guys hear me? Okay, so essentially, so is it fine now? Okay, so essentially, we're going to be running a Zoom, meeting similar to what you have during the lecture. And what you can, if you had a technical question that you want to ask in the exam without disturbing everyone else, so you either post a question in the chat or raise your hand in Zoom, and then one of the TAs will bring you into the breakout room, and there one-on-one, you can ask your questions with your voice. So treat it the same way as if you would normally raise your hand in the exam, and someone will come to you and you try to, ask a question, okay? So this is the way we're going to handle questions during the exam. So you don't disturb others. We're going to go into the breakout room. So try, if your question is relatively long, technical, try, and you don't think it can be answered quickly in chat, right? Then raise hand, say, I want someone's attention to ask question, blah, and someone will be going to put you in the breakout room and would answer your question there. Okay, is this clear? Okay, so this is the mechanism. So try to make it as close to as possible to the normal exam, so you can still ask questions live, okay? And as I said before, to avoid plagiarism, but not to discomfort you guys in the exam, because I've seen some other exams where they like super limit everything you can do. And it's very stressful for everyone because like TAs has to monitor every movement you had near the camera, and they don't want to do it. So what we're going to do, we're going to do selective oral verification. So after the exam, we're going to look and grade your exams, and if we had any suspicion, then we might call that person and ask them essentially to clarify that how they come up with the conclusions. And if you can't, then we would follow up on that, okay? So please, it's an open book exam. There's no need to memorize. Moreover, if you carefully study with what I show you today, there's no need to cheat in any form, right? You can do it yourself. Also remember, we're gonna, similar to the last few quizzes, we're gonna essentially replicate the problems. So essentially every problem's gonna have a lot of different versions. So it's like, if someone has an answer X on problem Y, it doesn't mean you have the same answer. It might, you're gonna have different parameters and everything is different, right? So don't get a poor grade just because you copy paste someone results and they're all for different questions. Remember, right? But all problems are going to have multiple versions, right? So work on your own version. Any questions about logistics? Is everything clear about the exam? Yeah, so the question is, when would those interviews be? So the interviews would be, we would need to grade things first, but I would expect that there would be the week after. I really hope we're not going to have a lot of those use cases, really hope. No one wants to be in this situation, but we need to make sure that things are fair for people that, are not involved in plagiarism. So it's probably going to happen the week after. Aidan, does it answer your question? I don't have the specific dates because we first need to grade and see the cases, right? Yeah, I'm doing, yeah. Well, I hope that's not too many cases. So obviously when we're going to schedule something with the student, we're going to take the exam schedule into account. So we're not going to randomly assign you one slot. We try going to pick some time when there's the minimum number of conflicts. And I really hope it's not too many people. Okay. Okay, any other questions about logistics? So can we have more detailed information on the exam, like how many multiple choice questions, how many writing problems? I don't have the specific number of how many multiple choice questions. Yes, there's going to be a bunch, maybe around 10 dozen. I don't have the specific, some medium size. Remember, guys, the way you write exams, it's not just specific number. We prepare some problems and then we do a dry run. We run those exams ourselves and see how long it takes. And we calibrate like with TAs, and then we try to calibrate for your speed, right? And then sometimes we need to remove some problems to make it shorter for you. But how many big writing problems? I expect 3 to 4. So there are going to be 3 to 4 large problems, a lot of small ones and some medium ones. And I'll give you, I'll show you examples of large problems today on different topics. So you get a sense of how large they can be. Make sense? Okay. Any other logistics questions, guys? Please don't be shy, ask questions. So it's the whole meeting today is about your questions to me. Okay. No more questions about logistics? Okay. Let's move on then. So resources. Essentially, we ask you, you allow, oh, there's one. What if we miss the message of oral interview because my mail app sucks? Don't overwork. We'll make sure that we reach you. So even if your mail applications has issues, we'll try different ways to reach you out, right? Or we'll send the message multiple times. So don't. So what I can guarantee you, we're not going to make any actions until we reach you, but you also cannot disappear. So if we're very suspicious on cheating, that the person cannot just disappear for a week, right? But we will make sure that multiple emails are sent, right, if needed. Does it answer your question? So you're not going to be just silently penalized because you didn't respond to one email, okay? That we can guarantee. So that's going to be happen multiple times. Okay. Any other questions about that? Okay. So you are. Yes, I've seen some of your cats once, I guess, on one of the videos. Okay. So we ask you to restrict yourself to materials linked from the course website, slides, reading guides, the textbook. Essentially, this is open book exam, right? And you are free to use the material that we covered in the lectures to your convenience. Remember the exam, and I like to make the exam this way, they're not about memorizing stuff, right? It's about understanding things. So if you don't remember, you know, the opcodes of something, you don't need to remember that. All these tables are given to you. You can use the slides, reading guides, this is all fine. So as I said, there's going to be a Zoom chat for clarification. So if you had any technical problems, I totally understand there can be internet connection, all these things. I really hope we're not going to have those big issues, but anything can happen. So please keep us updated. Like make sure beyond your regular Wi-Fi connection, you had your phone available and you can connect through your phone to the Zoom chat to tell us about what's going on, right? And we'll try to do our best to fix things. Not everything is in our hands sometimes, but yeah, I really hope the Quercus is not going to be down, like because that's possible as well. Okay. Another just piece of advice I have: the way I structure the problems, it's useless to Google them. I'm going to show examples today. You're going to understand why is that. So the question, the Zoom will be open during the test. Yes, the Zoom will be open during the test. Me and TAs will be sitting there to pretty much handle your questions. As I said, other clarifications to some problems or technical problems. So I would prefer people to start. We will discuss it with TAs. The problem, if you're going to start 1 hour later, it would be out of sync with other students. So the only reasons to start later, really, if you're in some weird time zones, but I would prefer you to start normal, as you would normal exams will start. The 3 hours is for any delays, internet connection issues. If someone's going to lose the connection, we reserve some extra time ourselves. But I want everyone to start at 8 p.m. Well, we would probably wait for a few minutes, right, before start. But essentially, I prefer everyone to start at the same time. So there might be some lags, obviously. I cannot, as a normal exam, I cannot enforce it, but you shouldn't start like 1 hour after others unless you had a super strong reasons to do so. Also remember there are also the reason 3 hours reserved, we also had, you know, people with special needs that they had extra time to write the exam. And I don't want that to go into the midnight, right? So that the time is reserved for them being able to finish it if they need it. So Jonathan, did I answer your question? You have 90 minutes to complete 90 minutes exam. So the timer will start, right? I'll discuss, and but we keep an extra time if you have any, because we understand some of you might have connection issues, like anything can happen, right? And if that happens, even if it's realistic, so we would check with you and then try to, we need to have some essentially spare time, right, to add if needed. So don't look at these 3 hours. That's what just for administrative reasons, I book a larger slot of time. So so they don't schedule you another exam interleaved somewhere, okay? But you expect 90 minutes exam, right? So you don't have 3 hours to complete a 90 minutes exam. The minute you start the exam, the click, the timer would go. Any questions? Okay. No question, no more logistic questions here. Okay, I'll go back to the slides then. So I said here, don't Google or search Stack Overflow. The reasons why is because you're going to waste a lot of time. You're not going to find the problems directly. We'll make sure they don't exist. And the way we're going to structure the problems, there's no direct answers to any of that. So if you're going to search, you're going to find something somewhat related, and then you need to study it. So it essentially would be the same as study to begin with. So you're going to waste a lot of time on the exam if you're going to search it. You can search for one problem, but then you're going to, negatively affect yourself. So exam is timed, so you don't have time for searching actively on the web. And there's not going to be direct answers to most problems. Questions? So you should do the exam by yourself, right? I think that's clear to everyone. So I don't have any past exam of my own because it's the first time I'm teaching the class. You can look up the versions of the exams that were taught, for example, in downtown, right? But they're not exactly the same as mine, right? So I'm gonna give you problems today, yeah. Yeah, someone says there's a SAM repo. Yeah, you can look at some older exams to practice if you want. But remember, all of us had a different style of teaching. So like the problem and the problems I'm going to pick are going to be different. Also remember that previously this course was with Verilog. So a lot of big problems that were asked in the exams that were related to Verilog, while we're going to have a lot of assembly questions. So there's no problem to study, but just remember there's going to be a different set of materials in those exams that we didn't cover, and we cover some other stuff. So just let me show you guys understand that. Because like previously this course at UTSC was always done with real boards. So there are a lot of questions about the labs and Verilog. Okay, any questions? So the good question, how much should we focus on the first half of the course materials compared to the second half of the course materials? I think someone asked that on Piazza. I reiterate on the answer. Essentially, the questions you're going to get are going to be from all parts of the course. The big problems, the ones that are more complicated, are going to be more towards the second part of the course. So essentially, and I'm going to show you, so essentially assembly, processes, caches, that's going to be your big problems, right? Because they're more exciting. But anything from the first part of the course can be in, obviously, it's going to be a lot of questions from the quick questions and also in the mid-sized questions. So like flip-flops, all of that would be also there. And say K-maps can be also part of the big problems. So there is a little bit of bias towards the second half, but you cannot just focus on one versus not focusing on the other one. It just the second half of the course has more advanced topics and it's naturally fits nicer into big problems. But smaller problems is going to be a lot of smaller problems is going to be related to the first half of the course. So Eddie, did I answer your question? Yes. Okay, and specifically, today I'm not gonna focus on small problems because you practice a lot of them. Your quiz essentially were the representative samples of small problems, so sometimes little problems, yeah. But overall, I'm gonna focus on big problems today. You're gonna get most of the grades for those, and those are the ones that are harder to do. Okay. Okay. Quintan will take your feedback as an input. We'll try to make them easier to read. Okay, any other questions about resources? So don't search for the answers. That's my just honest feedback. You're gonna waste your time and you're gonna regret that you spent 15 minutes on searching for answer one question. You're gonna find the exact answer and then you're not gonna have enough time to finish other questions, okay? And do it by yourself. You're not gonna lose your points just because you talk to someone and you get identical answers. Okay, so type of questions. It's a Quercus quiz, so similar to what you already have, just longer. In addition to conceptual questions, we would ask you to things like analyzing combinatorial circuits, including transistor diagrams, designing a combinatorial circuits, analyze the second virtual circuit or a waveform, design a circuit or FSM, and then set signals on the processor data path, explain how an operation is performed on the processor. That's definitely gonna be one problem like that. Translate assembly to machine code and vice versa. Write assembly code according to the requirement. So assembly questions definitely gonna be there, one of the big problems. Translate between assembly and pseudocode, count hits in a cache, analyze cache behavior. I highlighted that. We're going to go into these problems today again and again. That's an important topic, and I want to make sure you guys get it right. And say calculate throughput on a pipeline processor. So this is the type of questions you might get. I'm not saying which one you will get, but this is the list that you can clearly get. So how to study is I really make this class that there's no surprises, right? If you just study the lectures alone and do your labs by yourself, you would be ready. You would need to prepare, reiterate, review the quizzes, but I can guarantee you that there's not going to be any random questions you're not ready to answer. Everything that's going to be on the exam is something that I covered in the lectures and usually multiple times, okay? So whenever confused when working on certain problems, please go to Piazza. So one of the TAs will jump and help you, or me, when come to office hours, okay? So this is just my advice, right? So feel free to read any additional materials you like. That would help to enhance your knowledge, but really to write this exam successfully, you don't need anything under the lecture materials. Any questions about preparation? No questions? Okay. So some exam tips. Pay attention to details. When you prepare and go with the slides, there is a tendency just gloss over the slides very briefly, right? And get the basic idea. And that's not enough for the exams. You need to find a way to test yourself. You need to make sure they go into the depth and you make your hands dirty and practice the problem. The quiz questions are the best examples of the questions we will use, like especially for small problems, right? So make sure you study those. The questions in the textbooks are the next best. You can practice those as well. Make sure you had a good strategy for solving each kind of problem. For example, for assembly language, first write a pseudocode and then translate. That's a good idea to do. Don't try to write assembly from scratch. For design questions, create a truth table, then go to a K-map. So don't try to jump over stages, right? There's no need to do it, okay? So essentially for a different class of problem, make sure you try a couple of examples and you're comfortable doing it yourself. Okay, any questions before we go to some examples? Okay, let's do some practice. Again, before we go into that, can I at least make sure that some people would turn on your cameras? It would really helpful because right now this part needs to be very interactive because we're going to go through the problem step by step. I want to see how you guys react to that, at least some of you. Okay, anyone? I hope at least some of you can do it. We had 30-something people in the lecture. Okay, I can't really do much about it. Let's do whatever I can do it. So the first problem is the cache parameters. Yes, you can, but I mean, if someone is confused, I can't really see it, right? So it's a bit difficult with the questions. It's much more efficient with the video to read, you know, the nonverbal language. Anyway, it is what it is. Let's go. Let's go on. The first thing we're gonna go is your favorite cache questions. So I'm gonna give you two problems with them, two very similar problems, and try to do it with you step by step. And let's see how it goes. So, so the first problem is given a 128-byte cache with 12-bit addresses, that is direct map, and it has 32-byte blocks. Find the distributions of the bits that goes towards offset and versus towards tag. So do the math on the bits, essentially. What I need to know is how many bits it goes for offset, how many bits goes for the set number, and how many bits goes for the tag. Okay. And I'll show you the solution, but first I want you guys to start doing it yourself. So let's start, my advice, let's start with the offset. How many bits we need for the offset? I see two answers. One is 5, one is 7, another 5. Yeah. So the correct answer is 5. So, and it's relatively straightforward. And again, when you solve these problems and you're given the size of the block, right? And it's typically either a given number or something like a word, and word is like 4 bytes. So you know the size of the block essentially. And the number of bits is the log of the size. So to address the 32 byte, I need 5 bits, right, to represent that. It's relatively straightforward. I strongly suggest to do the offset first because that's the easiest part. So you already get rid of some bits, right? Remember there are 12 bits total here, right? Is this clear to everyone? I hope there's no questions there. Yeah, Sam, you are correct, but practically you're never gonna get caches that are not gonna be blocks of powers of 2, so sealing is not required, but you're right. Yeah, so no one will manipulate with the blocks that won't be, powers of 2 in size. Okay, questions? Okay, sorry. So the second thing, how many sets do we need? Set bits. So some people said, I see 7, 4, and 2. So I guess that's still not clear to everyone. Let's go over that together. I hope you guys at least think about it. So there is really, so this is direct map cache. What's the best way to think about it? I had a total of 128 bytes total, right? Each of these bytes are sliced into the blocks. So since they're sliced into the blocks and it's direct map is the most trivial type of cache, right? It means that I had each set as one block. So I literally need to take the number of bytes in this cache and divide by the size of the blocks. This is how many blocks I can have in parallel in the cache, just 4. So it means there are 4 sets, right? Yeah, Quentin, like 12 has nothing to do here. So the total size of the bit address only matters at the very end when you try to compute how many bits are needed for the tag, right? Before that, everything is multiplied directly without looking at the total number of bits by just on the given configuration of the cache. Okay, so the number of sets is 4. How many bits I need to represent that? Okay, thank you guys. So this part is clear, right? So the number of bits needed for the index is log 2 of that, right, of the set. So that's gonna give us 2 again, okay? And if it would be uneven, again, everything was gonna be nicely aligned, but if it's not, that would be a ceiling of that, as I think Sam mentioned before. But in this case, it's just 2. So now we know how many bits are needed for offsets. We know how many bits are needed for set numbers. It's a direct map cache. There is no like issue with ways, right? It's not set associate if it's direct map. So how many bits we need for the tag? Okay, so now it's straightforward. Okay, I went very slowly over that. I hope nobody is gonna make mistakes on that anymore. It's relatively straightforward, right? You start with the offset, then you go into the set. There might be some complications if you had multiple ways, right? You need to take into account because then you divide not just by 32, but how many ways you have here, but then you got the number of sets that identifies the number of, bits here, okay? Remember, which way you are in a set associative cache is not stored in your address. That's decided by the cache. You don't store this information in the address yourself. So that part, whether it's 2-way, 4-way, 16-way, doesn't affect the bits. The bits affect essentially the offset, set number, and the tag, right? And the tag is left over. Okay, any questions here? Is it clear to everyone now? So unless you already realize, you're definitely going to get a caching problem on the exam. So I want to make sure you guys do well on it. So be ready. Okay, so that was just a warm up, right? This is like usually a small first question, sub part of the big questions. Obviously, the next thing we need to do is to deal with the real addresses. So we want to manipulate with this cache. So for example, if there is an address like that, essentially 600 in hexamal as a request coming to this cache. How we process that? So the first step, you convert this into binary. This is the binary representation of this address. I hope this is clear to everyone, right? Why do I have 3 bytes here? Can anyone answer why there is 3 bytes here? Why there are no more, like there's no more upfront and zeros? Why I had just 5 zeros up front? Remember, this is continuation of the previous slide. Yes, thank you, Aidan. It's 12-bit address. 12-bit address is essentially, sorry, I said 3 bytes. It's not 3 bytes. It's like 1.5 bytes. It's 12 bits, right? So 4 plus 4 plus 4, exactly. So this is why this is how many leading zeros are here. Okay, so this is binary example. So how we slice it, remember, this is exactly how we slice it. These 5 zeros here are the offset, right? This is offset within this cache line, 32-byte cache line. It can be 601, 602, it still would be the same cache line, but then offset changes. Then these 2 bits in the middle are the bits of your set. Remember how many sets we got on the previous slide? So yes, 4. So essentially the set number can be 00, 01, 10, 11. So this is essentially, if you starting from 0, it's 0, first, second, and third. This is the last set, right? And this is your tag. And the tag happens to be all zeros. Okay, this is how you interpret the address. So essentially, this is the tag, the index, the offset. This is how you need to quickly slice the bits of your address. Remember, you don't need to necessarily always write everything in binary. As soon as you see the top middle bits for index, that's what matters, right? And the offsets are usually very easy to identify. Here on the next slide, when we're going to process things, to simplify your life, I'm going to write you the binary representation, not the binary, the mapping. But you can do it relatively quickly yourself, okay? Okay, so now I show you how one address is interpreted, right? Now we're going to do cache operation. So remember that the first cache we're going to deal with is going to be the cache that is essentially direct map. Direct map is basically one-way associative. You're absolutely correct. So it's as simple as it can be. The question to you guys, what is the replacement policy used for the direct map caches? Yeah, so several people said FIFO. Just to be honest, that even simpler than that. Really, when it's a direct map, everything can map only to one location. So it's just overriding, right? So as Zihan said, there is nothing even to think about. The problem of replacement really only comes up when you get more than one way. In the first way, you take the block and you just override it with another block. There is nothing to think about. There's no QU, right? First in, first out would make sense if you had at least 2 elements, right? Here, there's pretty no elements. So even though technically FIFO is not incorrect answer, but really it's very trivial. Okay, so this is just for everyone to understand how this cache is going to operate. So what I want to do right now with you is I'm giving you a sequence of addresses. I put it in a table, think about them happening one by one, this first, then this one, then this one, this one, this one, this one, and so on, right? And then, again, for simplicity, I already converted things into binary, right? And I wrote you what the offset is, what the set is, what the tag is, okay, for each address. So because that's a mechanical operation, I don't want you to waste time on that. I just want you to look on this table and go follow with me. But that's essentially how you, process things, right? And this is a bit like, I'm not necessarily going to have that many requests, right? But this is how you do it, right? Conceptually. Is this clear? Like what this table is for? Okay, thank you guys. So this is just to simplify for us to do something interesting. Okay, here I put a temporary working table where we want to keep information on what's in the cache versus is not. Remember, we already did the math with you. We figure out that we had 4 sets. So those sets numbered. This V stands for validity bit. So this is, we need to track which blocks were not used or not. So that's called validity bit. So you just put a 1 when the block is used, and otherwise it's 0. That's when the program starts, or when you flush the cache, it's first invalid. It means there's a garbage there, right? So you can't reuse it. So you know whether it's a hit or miss. That's important, okay? So what we're gonna do now, we're gonna do 1 by 1 accesses with you, right? And I'm gonna use a marker. Hopefully I'm not too slow with it. And as we go together with you, we're gonna mark this table and then clean it up again, okay? So, okay, let's go first. So the first access is 070. So help me to fill in this table. First of all, whether it's a hit or a miss. My questions for everyone. Yes, it's a miss. Yes, of course. So that's the first try we're gonna do, the first iteration. This is a miss. It's a miss, but we need to update the table. So which set do I need to update, guys, for this first line? So we are in this line right now. Yeah, exactly. Last, fourth, 1, 1. It's all correct answers. So what I'm gonna do, I put a validity bit here. What is my tag? What is the tag that I need to put here? That's correct. So if you guys don't mind, I'll just put 1 0 here, but it stands for all these 5 zeros, okay? So I hope you understand what I did. This is essentially means all these 5 zeros here, okay? Okay, let's go to the next block. The next block is 0, 8, 0. Is it a hit or a miss? So someone asked what V means, and V means validity bit. At the beginning, the blocks are invalid. So whatever is stored here is a garbage. As we mark it, we know that 1 means there's a valid information here. So there is a point for me to compare the tags, okay? Yining, did I answer your question? Okay, so second block, guys, where does it go? Is it a hit or a miss first? Is it a hit or a miss? Okay, everyone got it's a miss. That's correct. Which, if it's a miss, I need to put blocks into the cache. Where do I put it in? That's correct. I'm putting it here. And what is the tag? That's correct. Okay, you got it right, guys, so far? Okay, let's move on now a little bit faster, okay? So I hope you get it. And I'll only stop, so we move a little bit faster, and I only stop when there is something interesting going on, right? So third request. Is it a hit or a miss? Great, guys, it's a hit. Why is that? So if you look here, we're gonna get the block, right, that maps to set 1, 1, where I had a validity bit. And what we're gonna do, we're gonna get its tag, this one, and compare with the tag that I have here, and the tag matched. It's essentially their slight offset within the same cache block. So this is definitely a hit, right? So Yuran said, we need to override the data. Well, I'm not saying whether it's a read or write. And this essentially, it's the same block. So you really don't, there's nothing to, if it would be a store, I would need to overwrite. But if it's a read, there's nothing to overwrite. It's still the same information, right? So right now, I'm not telling you whether it's a read or write. The content could be overwritten if it's a store, but right now it's a hit in the cache because the information is already in the cache. For simplicity, you can think this being just a read, okay? Any questions? So we just hit into this block. So after that, we get another block, 190. So is it a hit or a miss? Sam, you're absolutely right. The offset is meaningless in that sense. What it really means, you brought 32 bytes into the memory, right? And then periodically you might update 2 bytes or 4 bytes of that memory, right? You don't really manipulate with the whole cache line, right? So the offset in this case doesn't change anything. Okay, so someone asked, if tag is the same, then it means it is a hit. If different, then so Jonathan, if the tag is the same, then it means it's a hit. If the tag is different, it doesn't matter. It might be a read or write. It doesn't matter. What it means, it's mismatches. So it means you need to take out old data and move new data. And the people who said it's a miss, you're all correct, right? Why it's a miss? Because what happens here is I happen to map to set 0, right? and I look at my tag here. Here my tag is 0011, and here I have 4 zeros and 1. So the tag mismatches. It means I take out the old block out and put the new one in, right? And so essentially I need an eraser. So I'm gonna remove that. And so essentially this is the new tag here. Is this clear, guys? So what's happened right now? For everyone? Please, if you're not sure, ask questions. Okay, if it's clear, let's move on. So then, sorry, too fast. Then the next line, 084, is essentially maps to the first block as well. And you see the tag is mismatches. So unfortunately for us, that data was replaced with this guy. So the tag mismatch. So what I need to do is essentially, that's a miss, right? I need to raise this again, right? And put a 0 here. Okay, so this thing, this is actually the same cache line as this one, but now it kicks out the data, okay? Okay, and then, so that's essentially a miss. Then another block arrives, 178. 178, is it a hit or a miss? Okay, that's a miss. And what I need to do, I need to update my tag. So my tag is now 10. Okay, a miss. Another access 08C. What we're gonna do here, we're gonna look at the first block. We're lucky the tag matched. It's 401, 401, right? And it's a hit, right? So there's nothing to overwrite here. There's just another hit. And then we get the address F00. Is it a hit or a miss? Okay, that's correct. It's miss. And what should I write in the set 0? That's correct. I need to write 4 ones and 0. Right? Okay. And the last access? Okay. The last access is a miss, right, as well. Everyone sees this, right? It goes to that address 064, goes to the tag, sorry, to the set 11, and the tag mismatches. The tag is 0 here, and here it's, you know, and here it's 10. So essentially what happens, that's a miss, and we just update it, right? So it becomes all zeros. Okay, any question to make the full pass through like all these accesses? So can someone compute the hit ratio here? So what is the hit ratio for that problem? Yes, it's 2/9, right? And if you ask for the miss ratio, it's 7/9, right? So that's essentially what happens, okay? So then, so Eddie said, when do we use offset bits then? So the offset bits are needed to know when you read the real data, right? So essentially, so to explain it, in reality, when you write your code, your loads are 4 bytes, right? Or 8 bytes, right? And stores, but the cache lines are larger. So the reason why this happens is for locality reasons. So you need the offset bits in the cache to know which data to read. But for the replacement, it doesn't matter at all. So only set and tag is used for cache placements, as Sam hits here. So offset is, in reality, when you build the real cache, it's needed. I need to know whether to read 0 byte, first byte, second byte, 18th byte of this cache line. But it's not needed for the replacement, right? So you see it's in the same line. So we had larger cache lines than the bait blocks that we read memory for due to spatial and temporal locality, mostly spatial. Another question, what is V for? So I repeat once again, it's a validity bit. At the beginning, validity bit is 0. It means that there's a garbage in the tag stored. And you had 1, it means that is a real data stored there. Okay. Okay, so guys, just in the interest of time, I'll go quickly over another pass. So this sequence of accesses actually can be in the loop, and you might do it again. If that happens, what's going to happen? We're not going to run the second pass over the same addresses, but now we're not starting with a cold cache where everything is empty and all bits are invalid. We're going to start with this situation. What I want you to show that because we're running for the second time, things can be now different. So first of all, let's look what happens, right? So the point I'm trying to make, if you do the same sequence, it might not generate the same sequence of miss and hits because there's already something in the cache and you're repetitively doing it. Okay, so the question for you, we are now did the full pass over that, and now we're doing the second pass over this whole sequence of addresses. So we're reading this again. So is it a hit or a miss? Okay, great guys. So it's a hit now, right? So this is why this happens, is because it's not a cold cache, and that's why validity bit matters, because we had this bit 1 here. We know that access comes to something with the content, right? So it's now a hit, even though I'm accessing exactly the same thing. So the previous state matters in the cache. And again, I let you practice again, but you're going to see that everything else won't change in this situation, right? I don't want to do it if there's really nothing interesting going on, so I don't going to do it again. But what's the hit rate if you do the second iteration of the loop? Yes, Sam, it's correct. So 3/9 or 1/3, right? So you see that there, if you do multiple times the same thing, that the first iteration have some cold misses, but after that they not be repeated. So eventually their hit rate might improve a little bit, but then it becomes steady. And for that to improve substantially, we would need to add associativity. And that's what we're going to do after the short break. So I'll let you guys have a 7-minute break until 12:10, and then please come back and we go over a few more problems. Any questions about that? I hope I went into. Okay, again, question about the V. V in the picture is a validity bit. For each set, we had a bit that tells whether it's valid. It means there's something useful stored that, and there's nothing stored that. At the beginning, you start with all V's being zeros. And if you put something, you put a bit of 1. Okay. This is an example of a direct map cache. You're correct. After the break, we're going to look at the two-way associative cache. Any other questions? Okay, then see you in 5 minutes. Okay, let's come back and do a few more interesting problems. Okay, let's remove the pen. Okay, so we'll do the same thing a little bit faster now, but now for a different cache. So the difference here is we're gonna have the same size cache, the same addressing logic, so it would be faster for you. But instead of a direct map, we're gonna have a two-way associated cache. So same exercise as before. We need to identify the bits for offsets first. Then we need to find the bits that goes for sets, and then how many bits go for the actual tag. So let's do one by one. First, how many bits for offsets? Yeah, so everyone got that. Nothing really changed. The offset only depends on the size of the block. And in most problems, giving you a hazard, if you even face it in the future, it's either the block size is given for you explicitly, like 32 bytes. Your caches on your laptops are probably 64 bytes. So these offsets is pretty much, easy to compute anywhere. No problem. Okay, a little bit more tricky part. How many sets we're gonna have in this cache? So one set, okay, and 6 sets. Thank you, Sam. It's 2. Yeah, Kelvin, you're right, it's 2. So there are still mistakes, clearly. So, but Sam already showed the right math. So it's relatively simple. There's just a little bit more complication than before. This is the total number of bytes you have. This is how many bytes goes per block. But now each set has 2 ways. So I can store 2 blocks there. So I need to divide not by 32 by 32 multiplied by 2. So the total number of sets is 2. And yes, you just need 1 bit for that. Is this clear? So this is really the only complication here. You need to take into account associativity. Okay, how many bits do you need for the tag? Yes, it's 6. Why? Because the total is, sorry, I made a mistake here. It should be 12 minus 5 minus 1. I apologize for that. So let me just, okay, so that should be 1 here. Okay. So yes, tag. Okay. Remember, guys, be attentive to the details. Anyway, you found all the configurations, right? So similar to last time, we can go through the cache operations once again. This time, that's how it's going to look like. Again, I prepared for you everything. So this is your tag, this is your set, and this is your offset. In the exam, you will have to do it yourself, right? But it's relatively straightforward, right, for the addresses, right? And then you have this new table, but you see this new table is a little bit more complicated, right? So we use LRU replacement policy, least recently used. So it's not exactly leap4, so it's least recently used, right? That's what I put it on the previous slides. Okay, so what's the difference now? There are 2 sets, but each set have its own way. It's way 0 and way 1, right? The numbers of the ways doesn't really matter. It doesn't really affect anything. So essentially, what happens, we had validity bits, similarly as before, because at the beginning, everything is empty. And then we had LRU bits. This is the bit that tells me what was the block that was recently accessed, first or the second. And because there's only 2 blocks, I just need 1 bit for that. Why that matters? Because I essentially want to know which way to replace next. Okay, so this bit tells me which one. I just need 1 bit of information. Okay, so let's go through this example. Again, the same addresses should help you a bit. And I will do it a little bit with you, but then you should be able to go and do it yourself. But at the beginning, is the first one is a miss or a hit? Okay, absolutely correct. It's a miss. So which set does it go? That's correct. So we're going here, and let's say we start with way 0, right? So we're gonna put the tag, for simplicity, I'll just write 0, 1. Oh, and I apologize. I need to erase that. I also need to send my LRU bit, okay? So at the beginning, it would be just 0 here, right? Because that's our least recently used block, okay? Then we get the second access, 080. Is this a hit or a miss? It's a miss, right? So that everyone understands this. Where that goes into what set? That's correct, it goes into set 0. Our set is irrelevant, so what I'm looking at is this thing. So the tag is 10. Any questions so far? I think it's clear. So let's move next. This one is easy, similar to before. It was a hit before in the direct map. So someone asked, do we always start with way 0? To be honest, it doesn't really matter. Like whether you start with way 0, like you can always renumber them. You need to start somewhere. So I start with way 0, right? So, but it doesn't really matter. Like the problem will happen when that you're out of ways, right? So it's the numbering of the ways doesn't really matter. In hardware, it would be implemented in a certain way, but for you, it doesn't really matter which way you go first. For hits and misses, it doesn't matter. Okay, so the third block, it just happens to be here, right? So it maps here, right? What could have happened, remember when I accessed this 6.8, that if I would update, if I read this, so first of all, it's a hit, right? Everyone understands it. But there is one nuance here that I want to highlight. So you see, I access this block. So that's resulted in a hit. If it would be another element here, I could potentially need to update the LRU bit because that was the least recently used, but now I just access it. So it's now most recently used. Then I would need to update this bit. So that's the difference on the hits in the direct map cache. You don't really do anything with the bits, but here LRU bits might change. Right now, nothing's to change because the validity bit here is 0, right? But LRU is the replacement policy called listen tree reuse that I covered several times in lectures. That's a bit here that tells you which way to replace next, right? So which one is the least recently used? So when I have 2 ways, when there is no space, and you will see this soon, I would need to decide which cache block to evict. And that bit would tell me what to evict, okay? Does it answer your question, Jonathan? Okay, let's go and see. So you keep going, then you got 190. 190 is a miss, obviously, right? When there is a hit, do we update LRU? Yes. In most cases you need. In this case, there's nothing to update. But there's a hit, you need to update LRU. Essentially, you promote something higher up and something else goes down, right? Something becomes less. Okay, so let's look at 190. 190 maps to which set? Set 0, right? And it has a tag 110. So it's a miss. Where do I put it? So guys, put me the location. Way 1, right, of set 0, that's correct. So 1, 1, 1, 0, right? And the validity packed is 1. So what should I do with my LRU bit? Well, in this case, depending on how we interpret the LRU bit, but in this case, this block, right, is the least recently used, right? And it's way 0. So I keep it 0, right? So there's no need to change it yet, right? Because that points, you might interpret it differently, but right now you put it at 0, right? So I don't change it yet, but eventually it would flip, right? There is some difference because we just start. After the cache warm up and there is no like invalid blocks, things would be just increment, decrement all the time. So let's keep moving, but you just need to keep an eye on it. LRU tells you what is the next candidate for removal. Right now, this is the next candidate for removal. LRU is least recently used. That's the name of the replacement policy. But the bit itself tells you what is the block that you touch last. So the name is least recently used, but the meaning is essentially what out of the all blocks in that set, what was the last time you touch, you assume that that's the best candidate for replacement. Okay, you're gonna see things moving forward first. Okay, next block, 084, is it a hit or a miss? It's a hit. And which way is it a hit? Way 0, right? So you guys notice that. So there is something I need to do right now. And the something is change my LRU bit, right? Why is that? Because now this guy was touched the most recently. So the least recently used guy is this now. So my LRU bit becomes 1. Is everyone clear about that? So if I would need to replace something from that set, this would be the one to replace now, because this is least recently used. Is this clear? How would it know which one is the next LRU? So I remove this complication for you for now, you just track it. In reality, the real hardware use simplified version of LRU, which is called pseudo LRU. This is not exactly like that, right? Yeah, but for simplicity here, you can assume you use a real LRU, so it knows which one. It essentially keeps kind of a sorted order. Here, it's very easy. You just flip the bits. You know which one was touched last, and you just flip the bit for two-way cache. Yes, so there is some special case when there's invalid bits, right? But after that, things would be straightforward. That's why I'm showing you from the cold cache. Okay, let's keep moving. You'll see it soon. So the next access, 178. The first question, is it a hit or a miss? It's a miss, that's correct. Where does it go? One. Okay, and we got a validity bit here. Do I update LRU or not? Do I need to update LRU bit? Yes, we don't need to update because we just inject that was invalid before, right? Okay, so now we finally fill in the whole cache. Now it becomes more interesting. So now we had 08C. Is it a hit or a miss? It's at a hit, right? In which way? Way 0. Okay, so the way 0 is still the hot one, right? So do I need to change LRU bit or not? Why do I need to change their LRU bit? So Eddie is right, there's no need to change it. So why, guys? This guy was the one that we didn't touch for a while. That was the most recent. So, and this one was telling that this guy is the least recent, the last we access. And we hit this guy, so this one still stays as the last one, okay? So LRU bit doesn't change. It's relatively straightforward. You only flip that bit of LRU if you touch the other way, not this way. With 2 ways, it's very simple. Anyway, it's a hit, and there are no updates here. I just hit into this block, and it was already least recently used. Okay. Okay, then we get F00. Is it a hit or a miss? It's a miss. Where does it go? Okay, now you see, now we had different opinions, right? Okay, first of all, it goes clearly into set 0. Everyone is clear about that, right? But which way? Way 0 or way 1? It is way 1, right? Why is that? How do we know? LRU, thanks, Sam. So LRU tell us that there's no space in this set. This guy is the most useful guy. It was frequently used, so I want to remove this guy. So what I'm gonna do is I'm gonna erase those bits, right? And then what I need is 4 1s and 2 0s, right? So I'm replacing it with a new one. 1 1 0 0. Guys, anything else I need to do? Yes, thanks, Yinin. I need to change LRU to 0, right? Because now that's the most recent block, not the least recent block. So I need to go erase the LRU. Okay, and make it 0, okay? And then the last thing here, is it a hit or a miss? It is a hit, right? Is it a hit into which way? Set is clear, right? Which way? Way 0, okay. And do I need to change the LRU? Thank you, guys. Okay. So we make the first pass. So how many hits did we get? So what is the hit ratio? Yes, it's 4 or 9, right? You see, two-way associative cache behaved much better than direct map. It's instead of 2 over 9, it gets us 4 over 9, so it's twice better hit rate. Again, now you can go into a steady state and do this again. I'm not going to go with you because we want to cover other problems, but I encourage you to try out. The slides will be obviously shared. So, and I also get you hit misses here that you can use for reference. So essentially you're going to get, similar as before, In direct map, you're going to have these hits, but they're going to be in general way more hits now. So that's what you're going to get. So you're going to get actually 7/9 in a steady state. So Jonathan asked, what does the graph look like if we have four-way associative cache? Essentially, you're going to have four ways, right? Each of them has their own independent text. And you're going to have a validity bit for each of them. And the LRU is going to have 2 bits, absolutely correct. So LRU needs to have an index of the least recently used. So essentially, it stores the index the way that I want to remove if I had to remove something. Would it be fully associative in that case? George is absolutely correct. If you had this configuration, that would be a fully associative cache, and I would be not particularly interested. But in a larger caches, it would be more interested. Like four-way for this small cache, it would be fully associative, right? Okay, any questions? In fully associative cache, it's where each cache block can go anywhere in the cache. Remember now, when we find you at the set, and you can go to set 0, 1, right? You cannot go completely different location. In a fully associative cache, there's no notion of set. Anything can go anywhere, right? Yeah, fully essentially is like one set. So you had complete freedom. Any block can go into any free location. There's no need to store set bits there at all. Set bits is just 0 bits. Yeah. So there's no sets notion. You can think about fully associative cache like one huge line, right? And each new incoming blocks takes whatever is free. If there's no free, you remove whatever the least recently used block and put it in, but it's complete freedom. Fully associative is very expensive to implement because if you want to do it for a real big cache, like megabyte cache, you need, when you do tag matching, you need to search across all blocks. So if you had millions of cache lines in the cache, you would have to do a parallel millions of comparisons, which is impractical. That's why in practice, fully associative cache is only used for very tiny caches. Okay. Your typical cache using your laptop is L3 is probably 16-way associative, and your L1 cache is probably 4-way associative. Okay, that's just for a reference so that you know what state of the art look like. Okay, questions? Because I want to try other problems as well, not just caches. But I really hope you guys learn this thing right now, and you kind of can repeat it at home if needed. Okay, any questions? Okay, if there's no questions, let's move on. Okay, the next thing that I want us to practice is K-maps. So here, it's a reverse thing. So the K-maps is given to you, right? So essentially you had, you know, not A, not B, not A, B, A, not B, A, B, and, you know, the same for C and D. And this is your K-map. And the first question here, the inverse of what you usually do, is for the Y, right? Fill in this corner map with the values, okay? So can anyone tells me what would be the value here? 1, okay. How about this one? Yeah, so it's relatively straightforward, right, guys? You just look at the table, there are 16 values here, you map it into the 16 values here. It's very straightforward process, okay? So essentially, this is the outcome. Why is this an invalid K-map? I think it's a very, I mean, everything is differed by 1. I mean, that's what should differ by 1, yeah. Oh, I see what you're saying. Yeah, I might put the notes in the wrong direction. I'm sorry. So this is the correct answer. I'll fix that and share the slides. I think when I copy pasted the table, there was something that was not properly copied. Yep. So essentially, if you look at the correct thing, so this should be flipped and this should be flipped. You see A, B, C, D is 1 and here it's X. So this should be, this 2 lines should be flipped, right? Okay, sorry about that. And essentially, assuming that we would fix it, this essentially flipped and this should flip, right? What should happen is that you want to draw, a diagram, right? So you see this one is correct, right? So I didn't, had this issue here because you see that there was some copy paste issue, but here this is correct. You see AB is here, right? And A not B is here, and same for this two. You flip them, okay? So this is essentially actually, it might be possible that we'll ask you to draw it, right? The same way here. Or in some cases, we might just give you some figures and say, select one. It's up to us. So we didn't decide yet. But it might be possible that we'll ask you to draw and upload this thing, right? Yeah, using Excel from all of you different, it would be difficult. The image would be the easiest thing to do. Okay, anyway, what I want to show here is in this table, what we do this mapping, right? So we have angles, right, that forms 2 by 2. We had this 1 by 2, and we had another 2 by 2 because we can interpret axes the way we want. And then the next question for you is give us the expression that optimized groupings represent. So I want you the Y out of this truth K-map table. So try to get the formula for Y. Yeah, Sam, how many terms should be here? Like overall, how many terms should be in the final? Yeah, 3. So just type all 3. So I'll give you guys some time to figure it out. So Sam, type an answer. How about others? I'll give you a few more seconds to think about it. Okay, I think we got a couple of answers. So as you can see, it's AC, right? Then not B and not D, and not A, not C and D, right? It's relatively straightforward. It's essentially for 2 by 2, you're supposed to get a term that consists of 2, right, values. And for 1, 2, you're supposed to get a term that consists of 3 values, right, with some negation. Okay. This is just serves as a reminder. And as I said, we might ask you just to output the final answer, but most probably if this problem for K-maps is a big problem, we might ask you upload an image, right? So we can see your thinking, right? Okay, but it shouldn't be that difficult to do, right? So you would take an image, then you edit it with whatever, any visual editor, right? And then upload the image back, or you can, print it, like anything that's convenient for you, right? You can do. Questions? Okay, This is not an example of a big problem or like a medium-sized problem, but I want you guys to do it because I've seen a lot of mistakes doing with manipulating the binary numbers, especially using 2's complement. So, so the question here, you need to perform 10 minus 17, right? Those are decimal numbers, as 6-bit binary numbers using 2's complement. So, and I want you to show each step, how you go and converting from decimal to binary, then how you convert into 2's complement, and then you how performing the subtraction, and then converting results back to decimal. So essentially, let's do 10 minus 17 step by step. So please send your results in the chat, and you don't need to send the whole answer, just you do the step by step. First, you need to convert decimal to binary. Okay, is everyone clear, like how to do it? So essentially 10 is 8 plus 2. So you had their 4th bit 1 and the 2nd bit 1. And 17 is essentially 16 plus 1. So this is the first step. 0, 0, 1, 0, 1, 0 minus 0, 1, 0, 0, 0, 1. So the next step is converting to the 2's complement, right? I'll give everyone a few seconds to try it out on your own. If you have questions about what we did right now, please ask, but it's a very straightforward conversion into binary. Then after that, we do 2's complement. Okay, so we got 2 correct answers, so I'm showing it here. So it's relatively straightforward, right? This stays the same, this one is converted, right? So first you flip all the bits and then you add +1. So you first get 1's complement, right? Which is like 1, 0, 1, 1, 1, 1. Sorry, 1, 0. And then 1, 1, 1, 0. And then you do +1 to get 2's complement. So you get 4 1s at the end. And then you do addition as normal, right? So you add up things. And that's what you get, 1, 1, 1, 0, 0, 1, okay? And then you need to convert this number back into decimal. First of all, is this a positive or negative number? Yeah, it's obviously a negative number. Well, first of all, you see 10 minus 17, you kind of know the answer, but also the sign bit is obvious here. So you know it's negative. And so essentially, if you take this into account, right, that's a negative number, then you get the value -7. Okay. Any questions here? Does everyone understand how we get -7? So can someone explain how I went from this number and get -7? So when we manipulate with the bits, right, and add things, we treat numbers as unsigned, right? So Sam, you can check what you had 7. Yes, you can, but then how would you know that it has to be 7? So essentially, one way, like I think the easiest way to just get a 2's complement of it, right? So trying can be quite funny, but essentially the bottom line here, you take this number, you know that's negative, right? That's 1. So you go and do a 2's complement of it. 2's complement, it gives you minus value. So if you're going to convert this into 2's complement, you're going to get 0, 0, 0, 1, 1, 1, and 1 here because you get plus 1. So essentially, you're going to get 7. So you know that your answer is minus 7. Is it clear to everyone? So when you get that, and you want to get, it's a negative number, you don't know which one, you do 2's complement. You can do what Eddie also did, but I would say what I propose is much simpler because you can have longer numbers. Yeah, so that's what I said several times in lectures. 2's complement is minus value. So you had x. If you do 2's complement, it's minus x, right? Yeah. So that's what we did here as well. That was minus 17, right? We do 2's complement, so we kind of push this minus into the value itself. Okay, any questions here? Again, this is not a big problem, but I've seen a lot of you are making mistakes in asking questions. That's kind of fundamental things for computer architecture and computer organization, so I want to understand this. So please practice. It was very easy to practice and come up with a lot of problems on your own, right? So you make sure you don't make mistakes. Okay. And remember, if you're asked to do intermediate steps, make sure you had all the intermediate steps. Okay, so let's do something more interesting. That's an assembly, but in a reverse way. So usually we ask you, given a C code or pseudocode of the problem converted into an assembly. Here it's the other way around. I don't ask you to actually convert it into C, but when I'm asking you, look at this code and try to find essentially what this code is doing conceptually. So if you would algorithmically explain what this code is doing, all right? And just to help you a little bit, you can treat this as an array, right? And this is like a length of an array, right? Or list, like whatever you're going to interpret. And this is the loop that manipulates with this data. So try to find what it's doing conceptually. I'll give you a few minutes, so that's not a trivial problem. So try to look at the problem, try to think about what it's doing, find there's the problem with assembly, it's doing a lot, and most of this is irrelevant, right? There's literally just a few lines of code here that has a meaning of what's really happening. The rest is just, reading, writing, data, comparing, right? So find those few lines that matters. And then based on that information, try to tell me what this loop is doing. Okay, I'll give you 2-3 minutes, and then I'll go with you over the code. So I don't want just the answer, what the answer in some register. What I want you is what it's conceptually doing. Guys, just a question. Everyone is clear what the problem is, like what you should answer? So essentially, the answer should be like, this is like, I don't know, sorting of an array or doing something, right? Finding something. So this type of the answer I expect. So you should see what conceptually the code doing and then try to identify it. Quentin, is it clear now? So essentially, I do the reverse. Usually I tell you, do X, like with an array, and here you get the answer. You need to understand what was the question. I can tell you that the problem is really simple. So there's really just a few lines that matters here. So Kevin said, finding the largest element of the list. I actually think it's very close, but I think it's not the largest, it's actually the minimum of an array. But you were very, very close, right? So for everyone else, in the interest of time, I'll just show, like most of the code here is very straightforward. It's not relevant to the conceptual thing. This is just to read the value of length, right? So the 5 length of an array. And this is to start reading the elements of the list. So these ones essentially reads into T2, stores the first element of an array. And then, you comments to the code next time. That's Jonathan, that's the whole point here, that you need to decrypt the assembly. Like when in real life, you're going to get a generated assembly in front of you. There's not going to be any comments there. The assembly is going to be generated. You would have to look at it and understand what it would do in a real code, what's going on in this assembly. So there is no one to write that comments for you. So anyway, this is just a header that just loads the right value, right? Yeah, so it's essentially, eventually V0 is going to be there, essentially the mean value. So we store the intermediate value into T2, right? So as you see, we sometimes replace T2 with T0, right? When it happens to be that there is smaller value. So T2 stores the minimum value, and then at the end, it moves to V0 before we exit. So Ivan is correct, so the T2. So this is a branch that checks T2 versus T0, so it compares the two current values, and then it branches over it to better if we don't need to flip, right? And there, this branch really means let's go to next iteration. And this is the replacement if it's smaller. Okay. So overall, there's a lot of code here. You can do move, but there is, like, we did it in a lot of other examples, that there's no need to create an instruction move if you can just add with 0, right? So there's no like special move here. You can use a move, but that doesn't really change anything. Adding with 0 is the same as move. Okay. Any questions here? So essentially, assembly. Well, that was assuming there was some function here. So we know where we jump to the return, right? But yeah, so that's irrelevant. It's like what's important is this part, right? Okay, do you guys got how it works? Okay. So again, for the problems like that, you definitely don't want to Google them. You would need to look and try to understand the code, right? And you need to very quickly like my way of thinking it is just, I look at this is a straightforward code. I kind of mentally cross it because it's irrelevant. I just remember that the current element is in T2 and that's what matters. And as I go, I keep reading into T2 the values. That's what I remember from this code. And then I look at what it really does, right? And it's just keep comparing with the current values. So you can get problems like that just for a different, for a different thing. Okay, another very important type of the problems that I want you to show one example at, and that's where you might most probably need to draw as well, is the data path. So essentially, you would need to show the data path that invokes your processor when you do certain operation. So here, we increment the program counter by the value in the register as 0, right? And I'll do it for you to show it, how it works, just one problem. And then you can, try a lot of different things you can think about. Pushing something from the stack, adding two values, you would need to know which path you take, right? It's testing your understanding. Again, those problems you can Google, don't waste your time. You just need understanding. So here, we need to increment the program counter by the value in S0. So it starts with the program counter. So I obviously need to take the value of the program counter that is then passed to what? It has to part. I want to get increment. Increment means addition. So it means I need to pass this value all the way to the LU unit, right? And then it goes from here. Why does it go through a 0 max? Because it's not coming from a register. It's coming from the PC. This is why this data path exists. And then that becomes the first parameter into my LU unit. Then I want to add something with the value in the register. How can I get it? I need to read the data from the register. So this is the second read port that gives the operand into B that would be then goes into LU. It goes into here, and after that, it goes right into this max, right, with 0 input, and then it goes into the add. And then the add will generate the results. And then where does it go? So the question is to you, whether the result goes. Thanks, Sam. So I want to increment the PC, right? So it means I need to go all the way back here, and through this max, I'll go all the way to update the PC. Okay? No black magic, everything is straightforward, but you need to be very attentive. And you might be given, one chart and asked to do 2, 3 of these problems, right? And we might also ask you to say which flags are set, right? Again, in your slides, you have the exact parameters and what needs to be set versus doesn't. Then you just say, this is 0, this is 1, this is X, this is 0, this is 1. This is like, if you do LU, you need to set an operation. So if it's add, it's 001 that would do the add. So someone asked, why not register? Because we increment the program counter. So it really means PC equals PC plus S0, right? So that's what the increment of the program counter means. So the result is the PC itself, not the register. If it would be a register, then we would need to go from, from this output and, back to the register file. So we would have LU output, then there should be a path here somewhere that would bring you all the way to the register. Like, I think this is the path. Like this, like right into the register. I don't have like them at the top of my head, but it's very, very straightforward. So I can just tell you something. For example, you said that you want to, for example, you had, say you want to do an add or say subtract, and you want to subtract, say 2 registers and write it into the memory, right, into stack. So what you would have to do is you would have to read the registers first. So you're going to read one register, another register, then set a proper LU instructions to make it subtraction instead of addition. But then the results won't go like into PC or register. The result would have to go all the way to memory. So you would have to, go here and then like stored in memory using the address that you have. So essentially, there's going to be a flag there. There's a flag for the first operand being the register, second operand being the register, but the results being like a memory, right? So then you store it into the memory. Okay, so those are the possibilities. Everything is straightforward. You just look at where it's stored. You look at the diagram. You see where this thing is on the diagram, and you see which path naturally brings you in there, right? Sign extension is used when you deal with short constants. Remember, if you want to shift or add with some small constant, you cannot just add with a small constant, so it needs to be sign extended. So that's where you use it, right? So you get when you get an instruction and it had a parameter like immediate value is a small constant. So then when you decode the instructions, you see that if one of the parameters is register and another one is a constant, so you need to pre-process this constant. So you see, that's why it comes from here. Does it answer your question? Don't we need to input the instruction type from instruction 15 to the LU? Yeah, I think Rakshit, to answer your questions, for the original problem where you increment the program counter, everything is internal, so there's no like necessarily even an instruction. But if there's an instruction in assembly written, you're right. You would also need to have a path from the instructions to tell you what type of an instruction it is. You would need to start with an instruction itself. I just kind of oversimplify things here. Instruction register is where you put the instruction. So if you're given an instruction explicitly said, go through all the way through the instructions and show the path, then you start with an instruction, right? You read the bits. So if you're reading like an assembly line saying this is an instruction, right? So then you start with an instruction. It always starts with an instruction, everything one by line. So this is kind of like boring to keep writing this again and again. So if you are, I answered Jonathan questions. To answer Eric, I'm late for the next meeting, so let me just quickly wrap up. So if you're doing A plus B, so it depends what your arguments are. If your arguments already registers, then you read from a register file. If it's a memory, you need to read from the memory first. So instruction register, Jonathan, is essentially where the instruction starts as you parse it, right? So you want to be very detailed, show that path as well. I'm not going to be too harsh on that grading, but essentially the key thing is this thing. And we might also ask you to send which parameters has to be set properly so you get the right values. Okay, this is pretty much everything I have. There is just one more small examples that I put here to show that you might be given like a small assembly problems like pushing the value on the stack or adding two values, and then you will need to write a few lines of assembly code like that. So this is, for example, pushing the value onto the stack. So you first, prepare the stack pointer, and then you write a store, right? So this is how you write onto the stack, right, with two instructions. Okay. Took us a little bit longer, but thank you guys. This is all the problems I want to show you today. Again, I just remind you on Friday is just a Q&A. So as you study and prepare, you can come with some questions. I'll try to help you as much as I can. And obviously good luck with your preparation and start to prepare early. Thank you. Quentin, if you had a question about assignment, please put it on the Piazza because I had to run right now. So the TAs will help you with the assignment to answer them. Or if you want me, yeah. So, and yep, yeah, they should probably just help you better than me. But if you need my involvement after that, just, you know, send me the post on Piazza. Okay, thank you guys. Yeah, on Friday, there's no extra practice. We practice today. On Friday, just your questions. Okay, thank you guys. Bye.